Welcome to ScaleUp University. Welcome to the course on designing data intensive applications. So, this is the lecture 8 of module 1. And in this lecture, we will be discussing human errors and operational reliability. So, first, let us look at the lecture overview, like what this lecture is about, what all we will be covering in this lecture. See, your system, like the data intensive application you will be making, it is not just code and servers. It also includes, so your system will be having codes and servers. Along with the code and servers, it will also include operators, like the human operators who will be operating your system or who will be using your systems. It will also include developers who will be developing your data intensive application. You might also be the developer. Your system will also include administrators and SREs. So we already saw that hardware fails randomly and software fails systematically. So if hardware fails randomly and software fails systematically, this lecture introduces the most unpredictable element, that is the humans. So system might fail because of humans as well. Because in real production system, if we talk about majority of the major outages, they are not caused by hardware or not by software but by human mistakes. So in real production systems, majority of major outages, they are caused by human mistakes, not by any hardware fault or not by any unknown bugs, but human mistakes, operational errors. That's why human errors and operational reality becomes very important, because any system you take, like data intensive application, if you are building, if you want to design it, then you have to consider human errors, operational errors. Because when we are designing applications or softwares, the ideal scenario, the assumptions we make is humans act correctly because humans are smart. They will act correctly. Procedures will be followed. Documentations will be followed. Documentation is read. And mistakes will be rare. But unfortunately, in the real world production scenario, the actual reality is humans do make mistakes. Humans are fallible because they operate under stress. They might misunderstand complex systems and they might misconfigure things. So, in designing data intensive applications, in designing larger systems, human error is statistically guaranteed. So, operational reliability means designing systems that assume humans will make mistake. So the idea is very clear that when we are designing data intensive applications, we have to consider the hardware faults, we have to consider the software faults, but we also have to consider the human errors and operational errors, because human error is inevitable. Majority of major outages are caused by human mistakes itself. So this lecture will teach you operational reliability. Like in this lecture, we will learn, like whatever data intensive application we are designing, we will keep in mind operational reliability, wherein we will design the system that will assume humans will make mistakes. And that is what this lecture is. So this lecture will talk about human errors and operational reliability. So if we look at the topics that we will cover in this lecture, we'll talk about configuration mistakes, deployment errors, accidental data deletion, why humans are the largest source of outages, designing systems to handle human errors, cultural component of operational reliability, core engineering philosophy. So all these topics we will cover in this lecture one by one. So this is the module 1, Trade-offs in data systems architecture. Lecture 8, human errors and operational reliability. And we are starting with the first topic of this lecture, configuration mistakes. So what are configuration errors? See, if we talk about modern systems, they're highly configurable. Like we can configure the modern systems like database settings, timeout values, replication parameters, memory limits, firewall rules, and load balancer routing. Now, configuration error means error in configuring, like a small mistake in database setting or timeout value. So that is the configuration error. So a small mistake in configuring the system. And this small mistake, so in modern systems, a small configuration mistake can cause entire cluster outages, security vulnerabilities, and performance collapse. So now we got an idea that okay, what are configuration errors? Modern systems are highly configurable. We can configure it, and if we make mistakes in configuring the modern systems, that is the configuration errors. Like we can make mistakes in database settings, timeout values, replication parameters, memory limits, firewall rules, load balancer, routing. And we saw how dangerous configuration errors can be because a small misconfiguration or wrong configuration can lead to the collapse of the entire cluster. It can lead to security vulnerabilities. It can lead to performance collapse. So why configuration is dangerous? So see, configuration changes, if we talk about, they are applied instantly. Because see, any configuration change you do, its effect you will see immediately. That's why it can be very dangerous. A small mistake in the configuration, the entire system might fail, collapse. They may bypass code review. They may bypass code review. Okay, this is very interesting. See, the idea is that like the data intensive application you are making, for example, you are designing, you will be testing the code because any software we make, we do the rigorous software testing. We do all kinds of testing, and let us suppose there is no bug in the software despite the system might fail. And how is it possible? If the software is perfect, no hardware failure, despite of that the system might fail because of configuration. So configuration error, it might bypass code review because while reviewing the code, we are totally unaware about the configuration. Configuration is something which is the deployment. The code is like a perfect software is ready. When we will deploy it, then configuration will come into the picture. There we can make mistakes, and since humans will be configuring, it will be more of like a human error and operational error, and it can be very dangerous. It can lead to the collapse of the entire system. So configuration errors, changes are often applied instantly, so its effect will be seen immediately. They may bypass code review. They affect all nodes simultaneously. Okay, this is also something very serious because we know that in distributed systems, we have the concept of replicas, wherein or the application might be running in multiple nodes. A small configuration error, it can affect all the nodes simultaneously, and they are hard to test fully. Configuration errors, many a times it might go unnoticed, so it is hard to test fully. So what are the examples of configuration errors if we talk about? Okay, so let us look at some real examples of configuration errors. So if timeout is set too low, then we will face retry storm. Because if the timeout is very low, like let us have 5 seconds, every 5 seconds a retry request will be sent. So it will lead to retry storm. And why retry storm? Let us suppose 100 users are trying to access a resource. And if the timeout is very low, what will happen is that those 100 users will keep on sending the request. They will keep on retrying, and after a point of time, the system will collapse. It will not be able to handle the retry request. So we call it the retry storm. So a small mistake in the timeout setting, timeout value led, it can lead to the collapse of the entire system. Replication factor set incorrectly. If the replication factor is set incorrectly, data loss risk might be there. Load balancer misrouting. Okay, so if load balancer routing is not correctly configured, it can be very dangerous. So what will happen that incorrect like directing the traffic, the load balancer will end up indirectly directing the traffic, which can lead to service loops or total outages. So the key insight is configuration is code without compilation safety. Yeah, that is very interesting because see, if I talk about configuration, it also is equally important in a system, but it can go unnoticed because the code, we compile it to check for syntax errors, and we do rigorous testing to check logical errors. Similarly, configuration is also very important. So configuration is code, but without compilation safety. Deployment errors. So what are deployment errors? Let us see. Okay, so see, the idea is that when can we get deployment errors? When we deploy buggy code, the code with some errors or some logical errors. So deploying buggy code will lead to deployment errors. Rolling out incompatible schema changes. Deploying partial systems, it can lead to deployment errors. Incorrect version combinations. So these are like examples of deployment errors. And why deployments are risky? Why deployment errors are risky? See, this is very interesting. See, the idea is that when we will be deploying, like let us suppose you are deploying a new feature, or you're deploying a code, a new feature, what will happen is that all the nodes, they may update at once. And if any bug is there, if any deployment error is there, that will get migrated to all the nodes, which can lead to the collapse of the entire system. Backward incompatibility may break clients. Backward incompatibility is something very dangerous because a new feature, it might be incompatible with the existing software. So when you deploy that new feature, you might see the system is breaking. Database schema mismatches may corrupt data. Yeah, so the database schema mismatches because the existing, the live system might be using a database schema. You did some upgradation, you forgot to update the database schema. So there will be a database schema mismatch. It might corrupt the data. So if we look at some classical scenarios of it, like let us suppose the code, it needs new database column. So while deploying, you just deployed the code, but you forgot to update the schema, database schema. Then what will happen is that the code expects new database column, but it is not there because the schema is still the old one. So here we are issuing a error because here, see, the idea is that there is no problem with the code because code is perfectly fine. Then the new feature you integrated, the you developed, that has nothing wrong. And here no configuration error is also there. Here the error is deployment error because while deploying, you deployed the code, but you forgot to update the database schema. So that's a deployment error. So that is rolling out incompatible schema changes, and it led to the deployment error. Database migration hasn't run yet. So the idea is very clear that code expects a new database column, but we forgot to update the database schema, or we did the database schema update, but it takes some time to for database to migrate these changes because you might be using a cloud service. It might happen, And in this scenario, the system will crash across all instances. So this is a classic scenario. And why this is systemic, that is very clear. Because see, deployment, if we talk about deployment errors, they are correlated, meaning to say that same binary will be deployed across all the nodes wherever the replica is maintained. So same binary is deployed everywhere, same faulty logic will run everywhere, and hence all the nodes will collapse and the system will collapse. So that's why deployment errors, they are systemic in nature. Accidental data deletion. Okay, so accidental data deletion is a nightmare scenario. So here what is happening is that engineer, let us suppose engineer, he runs delete from users, like a query, like users, let us suppose it's a table, so delete from users. Now what it will do, it will delete from users, like it might delete all the users. So a wrong query can delete all the users. And let us suppose the engineer, he's running this query and he's selecting a wrong production environment, a wrong environment, production environment selected, and backup is outdated. In this scenario, what will happen? The data is permanently lost because backup is outdated, no backup is there, wrong production environment was selected, and there if the engineer is running this query, it's a human error, and this human error led to the accidental data deletion, and data is permanently lost. We cannot recover it, and it's a nightmare scenario. So why this happens is, okay, so why such a human error might occur? Because of similar looking environments. So this is interesting that basically in production we use blue green environments, blue green deployments. So blue is the live environment and green is the test environment. Now both look exactly similarly. We have to keep both look similar, all the conditions, all the configurations. And because of similar looking environments, choosing wrong production environment, selecting wrong production environment is very common. And hence accidental data deletion is like a very dangerous human error, but it is very common also because of similar looking environments, because of insufficient safeguards, because of inadequate access controls. So this is very important, like access control is very important, and because of overconfidence, because of overconfidence. So if we look at the common forms of accidental data deletion, so common forms of accidental data deletion, so dropping wrong database can lead to accidental data deletion. Truncating wrong table may lead to accidental data deletion. Deleting wrong cloud storage bucket and accidentally overwriting backups. So these are like very common scenarios of accidental data deletion. So very important lesson for us is, so the most catastrophic outages often involves data destruction and irreversible mistakes, because data destruction can be a nightmare and irreversible mistakes can be a nightmare. So humans do make errors, they can make errors, and this is like a one very interesting scenario we discussed, accidental data deletion, and this is very dangerous also because data destruction can be very dangerous, irreversible mistakes can be very dangerous. Why humans are the largest source of outages? Okay, so now will discuss something very interesting. Why humans are the largest source of outages? So see, humans will be operating systems that are too complex in nature. And if we try to understand the complexity of systems, like complex systems, in complex systems, hundreds of services, they're running concurrently, thousands of configurations are involved, multiple runtime environments are there, and multiple teams are operating. So modern systems, like they are very complex in nature, hundreds of services, thousands of configurations, multiple environments, multiple teams. And interestingly, no single person is involved taking care of everything, rather team is working. And hence, human error is very common. There can be miscommunication, coordination errors. So that's the idea. Time pressure. So most of the incidents, it has been seen that it occurs under stress, at night, during high traffic, under business pressure. Pressure is something which is a very common cause of human error, because under pressure, under stress, or during late night working hours, very easy, it's very common for humans to make mistakes. During high traffic, during high pressure situations, so humans, they rush decisions, they may skip verification steps, they may assume instead of validate, and it can lead to crisis. So these are like very important scenarios we are discussing. Let us suppose you are designing a very big data intensive application which will be taken care by a very big team. So all this you should be very careful. Like your team might end up making mistakes. So these are like very common scenarios which we are discussing. Overconfidence is one of the reason. Like let us suppose an expert is there. He's overconfident that okay, this won't break. So even experienced engineers, they end up trusting intuition, skip small checks, believe this won't work. But unfortunately, complex systems, they punish assumptions. Complex systems, they want validation. Complex systems, it wants validation, no assumptions. So even experienced engineers, because of overconfidence, because of some laziness and overconfidence, they will just trust intuition, they will skip small checks, and hence it can be very dangerous. Automation paradox. Okay. See, the idea is that automation helps, but the problem is that automated systems propagate mistakes faster. Like any mistake in automated system, it can propagate faster. Misconfigured automation can be very dangerous. Misconfigured automation multiplies the damage. So if I talk about automation, faster mistakes multiply damage. So now it's very clear that why humans are the largest source of outages, because when dealing with two complex systems, humans will be coordinating in teams. There they can make mistakes. Under pressure situations, human can make mistakes. Overconfidence is one very serious issue which can lead to wrong assumptions and automation paradox. So the key insight is that human errors, it is inevitable, because these errors are something which we cannot control. It is inevitable. And why it is inevitable? Because humans cannot be perfect. They can do mistakes. Humans are imperfect. Systems are complex and operations happen under stress. So the core idea is that reliability must include operational design. So, so whenever we are designing data intensive applications, we have to assume humans will make mistakes, and we have to include operational reliability in our application, wherein we assume that okay, humans will make mistakes, and rather than preventing humans from making mistakes, we should handle those mistakes. That is the operational reliability. Designing systems to handle human errors. Okay, now how we can design systems that can handle human errors? So the first key principle is make errors visible, because visibility is very important. Silent mistakes can be very dangerous. So to make errors visible, systems, they must detect anomalies quickly, alert humans immediately, log all critical actions, track configuration changes. So what are the tools and strategies we can use to make errors visible? So we should have monitoring dashboards in place. We should have alerting systems. We should have audit logs, change tracking, and immutable logs. So the idea is very clear. Humans can make errors, that we know. Human errors is inevitable. So what we should do is that we should have visibility in place wherein we should make errors visible. And how we can do is that if we have monitoring dashboard in place which can very quickly detect anomaly, alerting systems which can immediately alert human errors, audit logs, change tracking, immutable logs. So the principle is, if something breaks, you should know immediately. You should know what changed. You should know who changed it. Now the second design principle is that make errors reversible. So reversibility is very important, because see, this is very clear to us that humans will make errors, humans will make mistakes. It is an inevitable fact. So if those mistakes are irreversible, then it will lead to permanent damage. So now the big question in front of us is that how we can ensure, like what are the strategies for making errors reversible, how to make errors reversible. So version to config is a very powerful feature. Version to configs. So any configuration changes we are making, it should be versioned, because any problem we can roll back to the previous version. Easy rollback mechanisms, undo button for operations, database backups. Let us suppose I have a database, I should take a backup before upgrading it to a new version. Point in time recovery and blue green deployments. So blue green deployments is something very interesting which we already discussed. Let us so what we have is that we have two identical production environment. So blue is the live initially and green is the test environment. Blue is the live environment which is handling the traffic, and green is the test environment. Now what will, and both are production environment only, same replica. Now any changes we want to integrate, we will integrate it in the green environment, we'll test it. And if it is working, then we will redirect the load to the green deployment environment, and in the blue we will make the changes. So in this way, zero downtime we achieved, and uh, any mistake, like any errors we see, it is reversible in nature, because blue deployment environment is already running. So the golden rule we should consider is, never design a system where a single command can cause irreversible destruction without safeguard. So this is very important. So any changes we are making, we should have a replica of the same system, so that any changes we made, any issue we faced, at least we have a backup, a replica version of it. So a single command can cause irreversible destruction without safeguard, that we should avoid. So that is the golden rule we should keep in mind. And the third design principle to handle human errors, it's limit blast radius. Now, what is blast radius? If I talk about blast radius is the scope of impact caused by a failure. Scope of impact. Like let us suppose a mistake can shut down the entire system, then it's a large blast radius. And if a mistake will shut down a small part of the system, then it's a small blast radius. So what are the techniques to limit blast radius? Canary deployments. So this we already saw in one of the lectures. So in canary deployment, what we do is that any new feature upgradation you did, you make it live, but don't expose it to the all the user base. So what we do is that we expose it to 1% of the user base, so that we are testing whether that new feature is able to handle 1% of the load. And if it is working fine, then we will increase the load. We will expose it to the 5% user base, then 10%, then 20%. Like that, we will keep on expanding its coverage. Feature flags. So in feature flag, what we do is that we use if and else logic. If feature flag is enabled, run the new code. Otherwise, run the old logic. Now, the good thing about feature flag is there that, let us suppose, from the dashboard you enabled a feature, and because of that the system is breaking. Then you can disable from the dashboard, and in the code automatically it will take care of that, because when the feature flag is enabled, code knows that feature is true. So new code it will run, new logic it will run. And if the feature flag is off, code will get an idea that feature flag is off. It will get notified. So it will run the old logic. So here, because of feature flag, no need to rewrite the code. Maintenance will become very easy. We should have access control. We should limit who can delete or who can run destructive commands. Environment separation. We should have clear distinction between staging and production. And rate limiting. We should prevent runaway retries. So the architectural insight which we can take away is isolation boundaries, wherein we should prevent cascading failure and we should contain human mistakes. That's very important. See, human errors we have to handle. We should make sure that it should not cascade. Rather, we should isolate it. We should handle it. And if we are able to handle or isolate human errors, then we can prevent cascading failures. So now it's very clear that we have to design our data intensive applications to handle human errors, because human errors are inevitable. What we can do is that we can make errors visible. We should have monitoring dashboards, alerting systems, audit logs, change tracking, immutable logs, so that anything goes wrong, we get to know immediately. We should make errors reversible by version config, easy rollback mechanisms, database backups, point in time recovery, blue green deployments. And we should limit the blast radius. Canary deployments, feature flags, access control, environment separation, rate limiting. And we should try to contain and isolate human mistakes so that we can prevent cascading failures. So that's the idea. And in this way, we can prevent or we can handle human errors. Cultural component of operational reliability. So see, the idea is that reliable organizations, they encourage postmortems. So what it means is that any incident occurred, postmortem is the written record of an incident. Like postmortem is a written record. It contains the impact of the incident, the action taken to mitigate the incident, the root cause of the incident, and the follow-up task. So that's the postmortem. So the idea is that reliable organizations, what they do, if any operational failure or human error it occurs, they write it down. They maintain a postmortem. So they document incidents and they avoid, reliable organizations, they avoid blame culture, wherein, see, blaming individuals is a dead end. So idea is that if a single person can take down a whole cluster by typing one wrong command, then the mistake is not of that single person. The fault lies in the system architecture, not the person. So this is very important. So reliable organization, they work with this mindset that if a single person can bring down the entire system by a single command, then the fault is with the system design, system architecture, and not the person. So reliable organizations, they avoid blaming culture, rather they keep on improving. They try to make their system more and more operational reliable, wherein they welcome human mistakes and they try to handle human errors rather than blaming humans. And reliable organizations, they improve processes after failure. So the idea is blaming individuals does not improve reliability. Improving system do improves reliability. So that's the main idea. Core engineering philosophy. So see, you must assume engineers will misconfigure systems. This we already saw. Developers will deploy bugs. Deployment errors will be there. Misconfiguration errors will be there. Operators will run wrong commands. operational errors will be there, human errors will be there. So these are something which are inevitable. We have to consider that, we have to assume that, we have to design systems which can handle such kind of errors. So therefore the idea is, the system which we are designing, it must be forgiving. Systems must be forgiving. Systems must be observable. Forgiving means we can reverse the mistake. Observable, we should keep an eye. Reversible and isolate damage. So the idea is very clear. If I talk about core engineering philosophy, if you are trying to design a data intensive application, it should have these engineering philosophy in place, wherein your application should be forgiving, observable, reversible, and it should be able to isolate the damage. So finally, we completed this lecture. So in this lecture, we saw that human errors are inevitable. Configuration and deployment are major risk points. Accidental data deletion is common and catastrophic. Operational reliability requires system level safeguards, and visibility, reversibility, and isolations are essential. So the core designing data intensive application insight which we can take from this lecture is, reliable systems are not those without mistakes. They are systems where mistakes do not become disasters. So I hope you got a very good understanding of the concepts which we discussed in this lecture. So do subscribe to our YouTube channel ScaleUp University for more such interesting lectures and courses. Thanks for watching. Thanks for your time.